In gold processing, getting the metal out of the ground is just the first hurdle. During the chemical extraction stage, called cyanidation, microscopic gold particles are successfully captured, but they end up locked tight inside the deep crevices of porous, black carbon rocks. On paper, this gold-loaded carbon is incredibly valuable, but to a refinery, it's functionally useless. You cannot melt it, and you cannot mint it while it's still bonded to the carbon structure. To break those bonds, plants use a process called electrowinning. It requires a precise, high-pressure environment to force the gold out, a task that historically proved difficult to manage safely because it involves mixing high-heat solvents with active electrical currents. Before starting the extraction, operators must verify the carbon's grade. This isn't a one-size-fits-all cycle. The processing time must be exactly calibrated to the amount of gold present to avoid wasting energy or leaving metal behind. The first stage is the comprehensive desorption tower, a vertical pressure vessel keeping volatile extraction chemicals contained. Within these specific middle chambers, the tower maintains optimal heat and pressure, ensuring the plant extracts the highest purity without losing material. Inside the tower, distinct mass transfer layers separate materials. Gold-loaded carbon is suspended above a collection basin. High-pressure steam and chemical pulp inject from the top, forcing down through the carbon. This high-energy reaction physically strips the gold particles away, washing the metal out. This reaction creates a concentrated vapor-liquid suspension called pregnant liquid. At this stage, the gold is mobile, but it is surrounded by volatile solvent vapors that are under extreme pressure. Step 2 is solvent condensation. The tower's internal environment manages these pressurized vapors, causing them to condense back into a liquid state so they can be handled for the next stage. These first two steps transition the gold from a trapped solid into a highly mobile liquid, ready to be pumped out of the tower and toward the final recovery phase. The pregnant liquid pools in the bottom storage basin, monitored until the concentration reaches the process index. A specialized pump then transports the liquid into the electrolytic cell. This begins pregnant electrolysis. Applied direct electrical current forces the dissolved gold to precipitate, forming solid particles. These newly formed solids are gathered as a raw material known as gold slime. Finally, the slime is pickled in an acid wash to remove impurities. The refined gold is then smelted and poured into ingots. The application of direct electrical current is the final trigger that completes the cycle, turning the liquid suspension back into a pure, solid metal. Looking at the entire pipeline, we see the contiguous journey from pressurized tower to electrical cell. The core innovation is keeping desorption and electrolysis entirely independent. Solvent vapors used in the tower never enter the electrical cell. By isolating those volatile vapors from the active electrical current, this design removes the risk of fire and toxic leaks. It solves the safety issues that made older, unsealed extraction methods so hazardous for workers. Because these steps are separated and the solvents are recycled within the tower, the plant achieves a much higher recovery rate, leaving almost no gold behind in the tailings. Modern systems add a layer of automation, using specialized sensors to monitor the seals and pressure levels in real time. This eliminates the guesswork that used to lead to operational failures. By isolating dangerous variables into a sequential, sensor-controlled pipeline, modern electrowinning transforms a once volatile industrial chore into a stable, highly efficient ecosystem.